Welcome to Derivatives Applied Part 1. Right, so here's our first question. If the current in a 1 microfarad capacitor is to be 0.1 milliamps, at what rate in volts per second must the applied voltage change? So the first thing I always want to do is look at the question and figure out what it is that's given and then figure out what it is that they're asking. So we know that we've got a capacitor of 1 microfarad. We know that that current through that capacitor is equal to 0.1 milliamps. And the question is asking for a rate. So whenever we see a question that's asking for a rate, we're thinking something dV dt, or basically a derivative with dt on the bottom. And it's asking for a rate in volts per second. So now we know it's dV dt, and that's what the question is asking for. So we can go to our formula handout and find the equation that most closely matches all of our givens and has basically what we're looking for. And we come up with IC equals C dVt. The current in the capacitor is equal to the capacitance times the change of voltage over the change of time. And then we can put in our givens. We've got 0.1 amps, milliamps is equal to 1 microfarad times dV dt. Solve for dV dt, and we get 100 volts per second. Now, there really wasn't any calculus in that question. It was all algebra. Right, here's example number 2. The magnetic flux in a winding of 600 turns varied as phi is equal to 0.5 t to the 3/5 in Webers, where t is in seconds. Find the induced voltage when t is equal to 1 second. So we know we've got a winding with n equaling 600 turns. The number of turns is 600. And phi is equal to 0.5 t to the 3/5. And it wants to know what is the induced voltage in 1 second, after 1 second. So we've got our V induced is equal to negative n d phi dt. And so now we will need to do some calculus. We need to take d phi dt of the original equation, phi is equal to 0.5 t to the 3/5, and then put that into the equation multiplied by the negative 600 turns, and we get a V induced of negative 180 volts. So if you need to see the derivative, the actual calculus, go ahead and pause the slide and go through those steps right there. Okay, example number 3, the mutual inductance between two windings is 0.2 henries. If a current I is equal to 11 t raised to the 3/2 amps flows in one of the windings, how much voltage V2 is induced in the second winding when t is equal to 0.001 seconds? So we know that the mutual inductance between the two windings is 0.2 henries. We've got a formula for I, and the question is asking how much is the induced voltage V2 after 0.001 seconds. So we find the formula V2 is equal to negative m di dt. So we know that the m, the mutual inductance, is 0.2 henries. Put that in the formula. Now we need to take the derivative di dt of the formula given, and then multiply that by the negative 0.2 henries, and we get a induced voltage V2 of negative 104.355 millivolts. Example number 4. If the current in a 30 Henry inductor changes according to I equals 0.02 t to the 5/3 amps, after what interval will the induced voltage measure at negative 96 volts? So there's our given in that first bullet point. Those are all our givens. This question is asking for how much time. How much time is it going to take to get to that negative 96 volts? So we've got a formula. V induced is equal to negative L di dt. So we put in the V induced of negative 96 volts is equal to negative, our L is 30 henries, negative 30 times di dt. Take the derivative of I, get di dt, put that into the formula, and now we end up with a T to the 2/3 is equal to 96. Now, this is, the algebra part in calculus is where a lot of people mess up, is the algebra. So this step might, if you're not super secure in your algebra, you might kind of miss this step. So in order to get T by itself, we raise the entire question or equation to 3/2, which means now you've got T to the 2/3 times 3/2, which that ends up equaling 1. So now I've got T is equal to the 96 raised to 3/2. And now mathematically I can put that in my calculator, and I can find that T is equal to 940.604 seconds.